Hello everyone and welcome to Code Confidence. Today we are going to look at the legendary problem, the two-sum problem. We will look at why this is an important problem in coding interviews and why this is asked so many times in so many interviews around the world. Let's look at the problem statement first and then we will discuss how we can solve it. Okay. The problem states that we have an array of integers, nums, and an integer which we call the target. We need to return the indices of two numbers such that they add up to target. Okay, so our input is an array of numbers and we also have a target integer. There are some constraints that we have been given, which is there is exactly one solution present and the same element cannot be used twice, which is to say that you cannot use 2 at the same index twice to add up to 4. The indices of the two numbers need to be different. We do not need to worry about the positions of the elements in the array, so the order of indices does not matter. Let's look at the constraints as well. So the numbers array has at least a length of 2, which means there will be at least 2 elements in the array. We do not need to worry about empty elements. And it can maximum go to 10 to the power 4. Each of these numbers ranges between minus 10 to the power 9 to 10 to the power 9. And so does the target. And we have only one valid answer that is present. The question also gives us a hint to come up with an algorithm that is less than O(n) square time complexity. We will look at both the approaches. Let's take an example and work through the problem first. Now suppose that we have an array like this. It has 4 numbers 1, 3, 5 and 7, and our goal is to find 2 numbers that add up to 10. One of the ways that we can solve this is by what we call the brute force approach, which means try every possible option and see if any one of them satisfies the requirement. How will we use it here? We can start with the first number, we can fix it and then loop through the array to see if adding this 1 to any of these numbers gives us the result 10. So we can say we can take a pair 1, 3 which adds up to 4, which is not our solution. Then we can take 1, 5. It is also not our solution. And similarly we keep on processing till we reach the end of the array. In this case it is 1, 7. Which also does not give us the solution. So what do we do once we reach the end of the array? We simply choose a different starting point, which is the next element in this array. So now we start with 3 and then repeat the same process. So next we will get 3 and 5, which does not add up to 10, but then 3 and 7 do add up to 10. Which is what we are looking for. So if we try every possible combination, we will eventually arrive at the answer, or we will know that no such answer exists. Now we are keeping track of the starting point, and then for every starting point we are moving through the array. So what we are doing in this solution is a nested loop. And in the worst case, we might have to reach till the end of the array to find the solution. So the time complexity for this approach is order of n square, where n is the length of the array. But we are not using any extra space here, so the space complexity will be order of 1. Okay? Can we do better? It turns out that we can solve this question in linear time by using a different data structure, which is a hash map. Let's see how. Suppose we keep track of every number with its index. We can do that using a data structure called as the hash map. Then when we move through the array, we can check in constant time whether the complement of the number is present in the hash map or not. Reduce the time complexity of this question to linear time. As an example, if we start with the number 1, we will check our hash map, which is initially empty, and see whether the complement of 1, which is 10 minus 1, that is equal to 9, is 9 present in our hash map. Is it? No, right? So we will add 1 to the hash map with its index, which is 0. Now our hash map contains the number 1, and then we move forward in the array. Now we reach at the number 3. The complement of this number is 10 minus 3, which equals 7. Now let's see whether 7 is present in the hash map or not. 7 is not present. So we need to move further. But before that, we add 3 to the hash map with its index. So our hash map is now 1, 0 and 3 with its position, which is 1. Now we reach at the number 5. Its complement is 5. Is 5 present in the array? It's not, right? So we need to move forward. But before that, we need to add 5 to the hash map. And we do that right here. The index of 5 is 2. Now we reach 7. The complement of 7 is 3. We check for 3 in the hash map and we find that 3 is indeed present. So we take the index of 3 from this hash map and the index of 7 from the loop counter, and we return the pair as the solution. This is the crux of this approach. We needed only one loop to solve this question, so the time complexity in this case will become order of n, where n is the length of the array. But the space complexity is no longer constant. We had to use a hash map to solve this question, which can potentially hold up to the n items, and so the space complexity becomes O(n). And that's why this question is so important, because we have two different solutions. One is great for space complexity because the brute force approach has O(1) space complexity, but its time complexity is order of n squared. On the contrary, the hash map solution has a great time complexity, order of n, but it uses extra space, which is also order of n. This problem teaches us what is called the space-time trade-off. If you optimize for time, you compromise on the space. This is the key takeaway for this problem. Alright, what is the better approach then? Well, most of the time, the hash map solution is what we will prefer. But there are situations where, for example, you have very less memory available, which happens in microcontrollers, for example. In those cases, you might want to use the brute force approach. Faster is not always better. Okay, enough on the theory. Let's go ahead and code the solution for this. Alright, welcome back. Let's now implement our hash map solution for the two-sum problem. We will start with taking a hash map. Let's call it scene, and it's a normal dictionary in Python. Now for every number, we will need to take its index and the value. So I will write it for I comma n in enumerate nums, we will check whether the complement of the number is in scene. So if target minus n in scene, then we have arrived at our solution. So we can just return I comma scene of target minus n, because the question asks us to return the indices and we are storing the value as the key and the index as the value for that key in our hash map. Okay. If it is not present, then we add the current number into our scene. So scene of n is equal to the index of n, which is I. That's it. That is our solution for this problem. As discussed, the time complexity for this is order of n, where n is the length of nums, and the space complexity is also order of n because of using this hash map. Let's run this code and see if it works. We have an accepted for all the example test cases. Let's submit it. And we have to wait. And we have an accepted as well. So this is the two-sum problem. Keep learning and let's go beyond syntax and beyond self-doubt. I will see you in another video.